All right, today we are going to look at bubble sort. We're going to start off with a very high level general idea of bubble sort, where the idea is really, it's all about the visualization. So we're trying to put the smaller items to the left and the bigger items to the right. And you can think of these as bubbles, or you can think of these as people standing in line and you want the shortest person on the left and the tallest person on the right. Whatever concept helps you visualize this the best is what you should be thinking about when we're doing this. After we look at the general idea of bubble sort, then we'll look at a more structured way of doing bubble sort, which is how you would actually program it. I'm not going to show actual code, because if you think you need the actual code, you probably need to go back to the basics for your programming language and look at how do I traverse an array? How do I traverse an array multiple times? How do I swap to variable values? Things like that. So let's get started here with the high level general idea. So the very high level idea of bubble sort is that if we are looking at two elements that are next to each other, if the bigger of those two elements is on the left, then those elements are relatively out of order. So we want to swap their locations. If we look at two elements where the smaller element's on the left, then that's the way it should be, and we don't want to swap those two elements. So we're going to be looking at all the pairs of adjacent elements. So we could swap these, we could swap these, we don't swap these, we could swap these, we don't swap these, and we could swap these. So for the very high level general idea of bubble sort, it does not matter what order you do the swapping in, as long as you only swap according to that condition. You'll eventually end up with the exact same result. So let's say that I want to swap these first. And I'm going to go through this kind of fast because it takes kind of a long time. Sorry. We don't want to swap those. So let's swap those. Maybe we swap these. And maybe next we go swap these. And then we'll swap that there. And maybe we'll swap these. Then maybe we'll go back here and we'll swap these. And we got this bigger one here that needs to get swapped with that one. And it's a bit bigger than that one. So we're going to swap those. And now we are done. And the reason we know we're done is that if we look at all the adjacent pairs, the smaller one is always on the left, so there's no more swaps to be done. So that's just the general idea of bubble sort. Now, the more structured approach, I'm assuming you're going to be using an array if you're going to be trying to program this. You can also do this with a linked list. If you don't know what a linked list is yet, don't worry about it. It's similar to an array. So when you're doing this in an array, you're going to have something that looks at an element and the element next to it, and you're going to loop through the array. So this could be an index for the array, or you could use a pointer or an iterator. There's multiple words that mean roughly the same thing. But that's what this green arrow is. And so as you're looking through this array, we're going to say if this element is bigger than the element to its right, we're going to swap them. So I kept the little bubbles here to kind of help you correlate this to the general example. But in programming, we are comparing the numbers. So we are saying, is 5 greater than 2? Yes, it is. So we're going to swap these. And then we're going to go next. We're going to say, is 5 greater than 1? Yes, it is. So we're going to swap them. I'm going to say, is 5 greater than 7? It is not. So we're not going to do anything. We're just going to go next. Is 7 greater than 3? Yes, it is. We're going to swap them. Is 7 greater than 6? Yes. So we're going to swap them. Is 7 greater than 4? Yes. So we're going to swap them. We're going to get here, and there's no more element to the right. So at this point, we are done with that first iteration through the array. Now, you may have noticed that by doing this in this order, that we end up with the biggest element all the way to the right. So we can mentally say that one is done. We're never going to actually swap this 7 with anything again, so we don't need to compare this. We don't need to compare with the 7 anymore. So what do I mean that? Well, we have to go through the array multiple times. So we start at the beginning again. We're going to say, is 2 greater than 1? Yes, it is. So let's swap them. We say, is 2 greater than 5? It is not. So we're not going to do that. Is 5 greater than 3? Yes. So we're going to swap them. Is 5 greater than 6? No. So we're just going to move on. Is 6 greater than 4? Yes. So we're going to swap them. And then when we get to here, we know that the 7 is in its rightful place. So we do not actually need to compare the 6 to the 7. We're actually done with this second iteration through the array. So mentally, we are checking this off. And as far as programming is concerned, we are changing the variable that ends the loop, essentially. So the loop first time goes all the way through. The second time it goes through one shorter. And then the third time it's going to go through, but only another it'll be 2 shorter, basically. 1 shorter than the previous one. So let's keep watching this. So is 1 greater than 2? No. 2 greater than 3? No. 3 greater than 5? No. 5 greater than 4? Yes. We're swapping those. And then at this point, we know these are done. So that means this third iteration through the loop is also done, and that third largest item is now in place. Now you may notice that the array is now sorted. That just happens to be true based on the starting locations of all our data. We have not actually verified yet that the array is now sorted. In other words, the algorithm does not yet know that our array is sorted. So we need to start over again. And we're going to say, is 1 greater than 2? No. Is 2 greater than 3? No. Is 3 greater than 4? No. And then at this point, we've got a couple options. So we can continue all the way till the end, which would be say no, no. That one's done. Go back to the start. No. And that's done. And then the last one has nothing to compare to anymore, so that one's done. Or, let me undo that. Or at this point, during each iteration through the array, if you keep a variable that keeps track of if you've swapped anything, then we'll get to the end here and we'll say, oh, we didn't have to swap any of these. So because we didn't have to swap any of these, we actually know that all of the rest of these are good. And you can exit out of the loops early because of that. So it saves you a little bit of time by doing that. In some cases, just keeping track of whether or not you swap stuff is going to take a small amount of time. So if you aren't able to actually save any iterations through the loop, then it'll actually end up being slower. So, but yeah, I don't know. It's going to depend on your data. But yeah, in practice, you're not really going to use bubble sort. It's more of a academic thing to learn how it works, get practice of converting this idea into a program. But bubble sort is pretty slow. So you're not really going to use it in real world scenarios. The only time I've really used it would be if I'm learning a new programming language and I need to sort something and I don't know the built-in library way of sorting something in that new programming language. It is very easy to program a bubble sort really quickly as opposed to some of the other sorting algorithms. Although they are faster to run, they're more of a pain to actually write the code for it. So, yeah, generally, you won't actually use bubble sort in practice, though. But the idea of it is still very important. Let's look at some last notes that I have for bubble sort. I'm not going to go into too much detail here, because this is the first sorting algorithm we're looking at here. But the space complexity of bubble sort, which is how much additional space does it use for like variables and stuff, is considered big O of 1 space complexity, which is considered constant, which means you need a finite number of additional variables. This doesn't change with the size of the original array. You just need a few variables, like you need the index that you're traversing through the array. You need like a temporary variable to do the swaps, and maybe 1 or 2 other variables. So, because bubble sort is an in-place, it's like completely in place in the original array that you're sorting. It's not using any extra space. It's not like you need to create another array or any other data structure to store values in to do the sorting. Other sorting algorithms can use more space, but they do that because it makes them faster. Now let's look at time complexity for bubble sort. Is big O of n squared, which means the time bubble sort takes is generally proportional to the length of the array squared. So if you have an array of length 100 and it takes 100 milliseconds to sort it, then an array of length 200 you would expect to take around 400 milliseconds to sort it. So an array twice as long will be essentially 4 times as long to sort it. So it doesn't really matter when you have a small array like in these examples, but if you're trying to sort hundreds or thousands of things, then this is very slow. Eventually, we'll be able to do some more direct comparisons with other sorting algorithms. But for now, you just need to know this is pretty slow. And then the last important thing for sorting algorithms is the sorting algorithm stable? And bubble sort is a stable sorting algorithm. But what does that actually mean? What that means is if you have 2 values that are the same, you want the sorted you want their relative order when they are sorted to still be the same. So the reason you want a stable sorting algorithm generally is that, say you have a bunch of people who have a name and an age. And let's say you want people sorted by age, but if they're the same age, you want them sorted in alphabetical order by name. So the way you can do this is you first sort them by name so that everybody's in alphabetical order, and then you sort them by age with a stable sorting algorithm. And that will put them by age, but anybody who's the same age will still be in alphabetical order. So that's the sort of reason that you want a stable sorting algorithm. Sometimes you don't care about that. So some algorithms are not stable, or specifically you'll see that there are a stable and a non-stable variant of the algorithm. So the unstable, I don't know if unstable is a proper word for this, but the non-stable version of the algorithm will usually be a little bit faster. So it's up to you whether or not you need those things if you need your sorting algorithm to be stable. So that's pretty much all I want to talk about for bubble sort. I'll make some more videos. The other main sorting algorithms to learn are, for the easy ones, they are selection sort and insertion sort. And then the more difficult ones are quick sort and merge sort. So quick sort and merge sort are a little bit more difficult to understand and to program, but they are a bit faster. Or depending on how much data you have, they are a lot faster. How much stuff that you're sorting. So we'll get to those eventually.